Okay. I prepared the presentation to show you not so much the progress of physics, but what we can do with what we have achieved. So the title of the presentation is, as you see, Physics and Society. So I will show you some of the examples. Of course, that there are many, many more. A part of those I will show you. But I chose some characteristic examples of the impact of the conquest of modern physics in our daily life. And part of them are, let's say, used more often, as I will show you some devices of localization like the GPS. Some of them, hopefully, are less used because they are, let's say, involving probably some health problems. However, as I will try to show you in the next tens of minutes, what's the situation is that the researches we are doing and the direct implication of our findings in terms of theory, but in terms of devices which we are using too, part of them, of course, are coming from our research in our laboratories. I hope you get already a kind of an overview of the lab, if not for else because you were doing these experiments today and you will do some more tomorrow, but as well because going to the canteen you have to step around, and you will see even more tomorrow when you will go to visit our accelerator. So you will really enter in and you will see what we are doing in this framework. So all these researches, which this is the accelerator, what you will see tomorrow. This is Daphne, an overview inside. You will really enter inside and we'll see how it looks like, a kind of accelerator, which is a collider, so where particles are colliding with beams of antiparticles. So for what concerns the fundamental research, our main goal in the next future, where we hope that some of you will join our efforts either from technical point of view, namely engineers or informaticians or, well, different ways to proceed in this direction, others as a physicist, we hope that we will succeed to go further in this long way started 100 years ago, where we discovered that the world around us is done out of atoms, and as I showed you and other colleagues have shown you even more, these atoms are having a structure which is done out of quarks. We still do not know whether quarks are fundamental particles, like, for example, representing vibrating strings in an extra-dimensional, multi-dimensional space, or maybe they can be divided in smaller pieces if would have a stronger accelerator. You have as well seen that a part of the particles which are composing our so-called normal matter, there are others in the framework of standard model, in the framework of standard model, which you have seen in the last days, which are composing other particles like the kaons inside Daphne, like the Higgs boson, but as well there are many mysteries, and you have seen from Anthony Palladino the dark matter and the dark energy, the first one supposedly being composed of particles which we didn't discover yet, particles which probably do not stay in the standard model, but they might be either supersymmetric particles or something else. So it's still a lot of things to do, not to speak about the dark energy, which is somehow the biggest mystery, as I was saying this morning, of the present day physics, because we have only very vague ideas of what it might be. And we know already that some of these ideas are not really fitting well, because they are many orders of magnitude far from what would be necessary to explain this dark energy. So from what concerns research, we are expanding our knowledge in both sectors. One, in the understanding of the universe, or if you wish, in the visible part of the universe, because it's very likely that the universe extends, the one that we see, it's very likely it extends far beyond what we succeed to see. and there are regions which are not related, so the light did not have yet time to reach us from these very far away regions. Since the Big Bang initiated, we can imagine it initiated, well, in regions which are far beyond our present reach. So on one side, we are expanding our knowledge on the universe, seeing many new objects and understanding much more, like black holes or, well, stars, which are nowadays there are many interesting features, like one of the questions which is posing is which is the possible mass of a neutron star. And even if a neutron star might seem an object which is easy to understand, in the end we arrive to the conclusion that this is not the case. You have mostly seen these days things coming from the micro-universe, standard model, the particle physics odyssey, the Higgs boson, and the quark-gluon plasma, future, let's say, facilities, a part of CERN, like the FAIR in Germany, which will offer probably to some of you the opportunity to go and to dig into the structure of micro world in this sector. And you have as well seen that our experiments today reached really impressive, not only dimensions, but complexities as well. This is ALICE, you have seen more, this is ATLAS. You have seen more details in the presentation related with the detectors. You have seen as well why we need to sandwich many different types of detectors, because what we want to do is to study different types of particles, and they are actually interacting very differently in the matter, so we need these dimensions. So all this knowledge, this is a view of inside ATLAS, and you might see here, well, the magnet. You have seen why we need a magnetic field, and that there are different types of magnetic field, and well, the goals, the aim of these particles. As well, this is in Italian, but it's easily to be understood, Angels and Demons, which was, which is a book of Dan Brown, which created quite an interest in the world. I start from here to explain you the physics and society. I choose to start from here, so from a, I don't dare calling it a science fiction, even if I will show you that in some way it is a kind of a science fiction book, but based on some real feature. The real feature on which it is based is the presence and existence of the antimatter. So the antimatter, we know, we can produce it nowadays, it's a reality. So there are a part of the particles which we are used to, like electrons and positrons, a kind of their brothers, which have, among other things, a different electric charge. So the positron has a positive electric charge, while the antiproton has a negative one. It might seem curious that we then define the antineutron, because one might think the neutron is neutral. What's the meaning to call it antineutron? Can someone answer to this question? Oh, raise your voice. Hugo, loudly. Right, exactly. So the neutron has a structure done of quarks, while the antineutron done of antiquarks. And this defines why it is an antiparticle and why it's not equal with its particle. Differently is the case of photon, so there are many, many still interesting items to dig into, but it's a reality that we can really build atoms done of antimatter. This is the example of the antihydrogen, which nowadays started to be copiously produced at CERN. Not at Large Hadron Collider, but at some other accelerators, because at CERN we have a complex of accelerators. Part of these accelerators are used to generate antiprotons. In this case, oppositely from Large Hadron Collider, we need very low energy antiprotons, because this antiproton should capture an anti-electron and form and shape this antihydrogen. And this is one of the things which at CERN it's studied intensively. It's a very difficult situation, because as soon as you generate an atom of antimatter, this one would meet so being neutrally, the atom itself, neutrally from electrical point of view, it's very hard to keep it stable, isolated from the matter. So sooner or later, it will diffuse and it will annihilate with the surrounding matter. So much then you gain in the energy that if we would be able, what was contained in the book of Dan Brown, to really create 0.5 gram of antimatter, this would annihilate and would make it annihilating with the matter. You'd have the same potential energy of the explosion as an atomic bomb, nuclear bomb would have. So by this point of view, the book of Dan Brown was somehow realistic. If indeed you would be able to manipulate and keep stable such a quantity of antimatter, this would be a very interesting feature from physicists, because then you could study it. But on the other side would be a dangerous problem if you wouldn't be able to handle it. But this would make it, now I don't want to spend too much time, but this is one of the reasons for which somebody might even think that it could be used as a propellant for the future space exploration. If you would be able to build a rocket which is working with antimatter, you would need a very small quantity if you would be able to handle it in order to send you in the deep space. But you see, where comes the science fiction part is the fact that with our present day best technique, even more than our best technique, because we are not able to keep it there. So even if we would generate it, we wouldn't be able to keep it there. You would need billions years. So in order to really generate 1 gram of this kind of antihydrogen, you would need billion years. However, now I want to show you a very interesting use from the medical point of view of the antimatter. So now I go from the studies of particles and antiparticles and standard model and beyond standard model. I go to show you what actually has been applied and it's presently applied in the hospitals as a technique which became, even if not used in any hospital, still used in many hospitals, a very interesting technique in order to unveil the tumors. So the technique is called positron electron tomography, and as you see right from the title, it carries in it the notion of antimatter, so the positron. By the way, here we have to pay again a debt to Dirac, to this excellent physicist. There is a very nice book, if somebody wants to read it, speaking about his discoveries and about his personality. It's The Strangest Man. It was translated in Italian as well, I think, as L'uomo frustrano or something like that. We pay a debt to him because he was somehow, I think it was already said last day, he was inventing the antimatter. When he was trying to describe in an equation what happens with the electron, where you consider the relativity, so to try to write an equation, relativistic equation describing the electron, he perfectly succeeded in this, but it was a problem. The problem was that this equation was similar to a second-degree equation, which all of you know how to solve, which is known to have 2 solutions, right? So in this case, he too got 2 solutions. One was obviously the electron. The second one was embarrassing him in 28, because everybody told him, look, that your equation has 2 solutions, and since in reality only 1 particle exists, it should be wrong. And he was trying to dump the second solution longly. He was trying to hide it somehow. And only in 32, you have seen the anti-electron, the positron, was discovered. So 4 years he was living with this burden of being, well, somehow victim to his success. But you see, so in the end, the positron not only exists, it can be used in this technique, which I'll try to briefly explain it to you now. So now forget a bit about the slide and try to follow me. So when a person is somehow supposed to have a tumor, moreover in a place which is not of easy access, so it's not on the skin, it's not on a leg, it's not on an arm, but it's in a very sensible place, like the brain, Of course, doing a biopsy, which might be the most natural, the easiest, and more direct way to check whether it's a tumor or not, in this case, it's very dangerous. By doing this biopsy on the brain, you might kill the person and arrive at the conclusion that he did not have a tumor. So in these conditions, mostly in these conditions, what happens is that you apply this technique that I'm describing to you now. So to the patient, this technique actually, it's a perfect example of a synergy between physicists, medical doctors, biologists, engineers, and all this community has contributed in specific ways to create it. So what happens in these cases? In these cases, the patient is given to drink. It's not the only way, but I describe you one of the most common ones. So the patient drinks a solution of sugar. So he drinks this sugar, which is not a normal sugar. So you don't go to the bar and take this normal sugar and put it inside. It's a slightly radioactive sugar. So this sugar contains atom of carbons. Do you remember how a normal atom of carbon is done? The usual isotope has 6 protons, which defines it as a carbon. But normal, stable carbon, how many neutrons it has? 6, right. In this case, what you do is you put inside this sugar, you modify it, and add a small quantity of radioactive carbon, which has only 5 neutrons. This type of carbon, it's not stable. It gets decay, radioactive decay. I'll come back afterwards. And since it's not stable, you don't find it in nature. So before doing this sugar, you have to produce it. So you use some accelerators before producing this sugar to have this radioactive carbon. So you produce this radioactive carbon in some nuclear reaction in some other accelerators. You put it inside this sugar, and the patient drinks this sugar slightly radioactive. Now somebody might be worried. I drink radioactive carbon, I die. Well, the quantity of radioactivity, it's very small. It's similar to the one you get when you go to the dentist. So you do a tooth radiography. Or if somebody of you broke his arm or his leg, is there anyone who did this? Who suffered an X-ray radiography? Nobody? One? Wow. 2, 3. Oh, okay. Now we are in the normal statistics. Good. I was worried you don't do crazy things, but since you are doing, now I'm back to the normal life. So this guy or this woman is drinking this radioactive sugar, and now it's in his belly. Why on earth would somebody do such a crazy thing? Now we have to go to the biological, medical part, which is the main characteristic of a tumor. So what makes it to become so aggressive, so crazy, and so dangerous? That it grows. Speak loudly. It grows too fast, exactly. So it overtakes the normal tissue, it grows uncontrolled. What means a tissue is growing? It means that it has a metabolism, right? Cellular metabolism. So in order to grow, it needs to eat. What is usually eating a normal tissue? Sugar. So when the sugar arrived in the belly, what happens? It starts to be transported to the organs or to the tissues which are requiring it. Of course, all the tissue are requiring it. We are not dead, we are moving. But the most quantity, it's mostly required by the tissue which has a tumor, if any. Right? Is this clear? Because this is the main ingredient to understand this technique. So the sugar goes everywhere, but goes mostly, because the tumoral tissue is very greedy, it goes mostly to the tumoral tissue. Once the sugar arrives there, now I'm a bit oversimplifying because the radioactivity, it's a continuous process, but with a lifetime decaying in time. But now let's assume that this is not really the case. However, so once the sugar arrives in the tissues, this carbon, this quantity of carbon, which is radioactive, so it doesn't remain like there forever. Usually, the time of decay, it's chosen to be rather short, so of the order of hours. Because if the time is too long, the patient should stay in the hospital forever. So if it doesn't decay fast enough. If it decays in 2 minutes, you don't succeed to arrive to do the sugar and the solution. So it's pointless to produce this radioactive substance. So you need to choose those type of isotopes which are having a lifetime, so which remain radioactive, with a time span of some, let's say, hours or days or something like this. And this is a very clever and independent research path. So once the carbon, this substance, this sugar, arrived in various tissues, the carbon atom decays, the carbon nucleus decays. It doesn't like to stay, it's not stable. This isotope, it's not stable. And it decays into a nucleus of boron. We don't care, so the boron remains there, it's not dangerous, emitting a positron. So the positron, this is a way to write a positron. You can either write an E+, it's an electron with positive charge defined as a positron, or we can write it as a beta plus. Beta plus defines the type of decay, which is a beta plus decay of this nuclear species. So it emits a positron. Okay, now we have a positron which was emitted. What happened with this positron? It won't go too far. Loudly. Right. It immediately annihilates with the first electron it meets. The first electron is extremely near, so it's in the tissue where it's emitted, the positron. So, so we have immediately in various tissues which were asking sugar, we have annihilations. More or less intense depending on how much sugar arrived there. In this case, in a tissue which might have this tumor, there are many annihilations. In this case, as a product of annihilation, I jumped these steps, they are not important. In final state of the annihilation, after the electron and the positron collide, they are generated 2 photons. So this is what is coming out. This is a similar process to what happens in Daphne. Here too we have electrons and positrons. But in the case of Daphne, they have much, much higher energy. So having much higher energy, we can create other particles in the final state. Here they are almost stopped. So we don't have enough energy to create kaons or whatever strange physics. But basically, the process is the same as what we have in Daphne, a part of the fact that we have to scale it down in energy. So we have in the final state 2 photons. 2 photons coming from the tissue where the annihilation occurred. If we have 2 photons emitted simultaneously, so the emission is simultaneous, and we detect them, and I leave you time if it is not obvious to think about as a homework, we are able to fix the point where it was generated. So it's 2 photons that we know beforehand that are simultaneously generated. Once we detect them and we detect the timing of their arrival, one might arrive sooner, one might arrive later, by the time difference, we can build the point where they are coming from. So we can build a map. How we detect them? With normal detectors, particle detectors, in this case radiation detectors. In this case might be crystals, for example. So forgetting about the fact that we look at biological effects, we can say that this is a physics experiment. It's like Chloe at Daphne, a part that it's on our body, detectors are similar, and the annihilation process is similar. But it helps us to build a map of where the sugar was mostly eaten inside the body. And this is how the apparatus look like. So you see that there are a series of detectors which are surrounding, in this case, the head of the person. As I told you, it's mostly applied for the brain, where it's difficult to do a biopsy. And inside here, there are these detectors, which are detecting the positrons coming from the annihilation of, detecting the photons coming from the annihilation of the positrons generated from the radioactive decay of the carbon contained in sugar. And you build, this is, let's say, how it looks like outside. So the person should stay here some time period. And there are computer programs, so that's where the informaticians are coming into play, which are building on a screen all the information coming out in real time. So you don't really need to wait 2 months to have the exit of these results. And that's what you get. You get a map of colors. Some of them are, let's say, more hot spots. And these hot spots are the dangerous points, because it means that in that places, annihilation occurred much more frequently, which means that there was much more sugar going. So the metabolism was much more intensive. And then it's likely, there are some standards, medical standards, where you know that above a certain threshold, here there is a tumor. You can see where it is, you can see how big it is, and then the medical doctors can decide how they come into play to cure it. So this is the method which is called positron electron tomography, and it's very widely used nowadays in hospitals to unveil the tumors. By the way, it's used not only for the tumors, it's used for many other functionalities of the body. In that case, you only need, and that's not a trivial matter, it will be one of the very interesting items for those who want to do genetics or biology. What you need to do is to find the marker. So in the case of a tumor, you use the sugar because you use the metabolism. If you want to see some genetic process, you still can put inside the radioactive nucleus, but you have to bind it in an active substance for that process, genetic marker or whatsoever you want to study. So this is a very clever interaction between physicists on one side, geneticians and doctors and whatever, and it's a very active field. So the game, it's only started to find that markers which go there and unveil the process you are interested in. I pass now on at another sector, another type of medical application, which looks somehow similar, but in its functionality, it's very different. It's the so-called computerized tomography, which is used not to unveil the tumors, but to make a photography, a three-dimensional photography of what's inside your body, whatever it is. So you might have some, let's say, some defect, some physical defect or whatever. You can see it. So let me jump on this. This acts, so here you don't have radioactive nuclei or whatsoever. You have, however, an X-ray tube, similar to the one which is used when you do the dental radiography or when we discussed before the hand or broken legs or broken bones. So you use the same type of X-ray tube. X-rays are nothing else but photons. Photons which are having energies thousands times higher than the visible light. So that's one of the reasons for which they are used. The visible light, we are not transparent to visible light, we stop it. The photons of higher energy can arrive to some depth in us and be either, well, we can either be transparent to them or absorb them. And playing with the energy of these photons, you might build a map of the things which the photon meets. If it is a bone, it's more likely that the X-ray is absorbed, like in a radiography of hand. If it is a soft tissue, it's more likely it passes through. So playing with these games, and again, adding knowledge from medical doctors, from anatomy, and from informatics, you can build an interesting map of the region which is studied. In this case, there are many geometries. One of the most used one, it's an X-ray tube which rotates. You have on the other side a detector of X-rays. So you study what happens, which is the absorption in that spot of the X-ray tube. So you do on an helicoidal trajectory, and you study what's absorbed and what is passing through. It looks similarly to the PET, but inside it's very different. So this is the apparatus. You can roll in and out the patient, And this is what you obtain. So you obtain really a picture of what it is inside us with very, very refined details. So you can check whether there are some defects, whatever, genetical or functional or, well, so this is really an amazing technique. This technique was not only used, it's not only used in medicine, but was, and it's continuously used, for example, to unveil some older mysteries. In this case, we have the archaeology, and was used to find the reason, or at least to exclude a possible reason of that of Tutankhamun, which, well, was, since he died, I don't know if you know, he died at 19, very young. It was at some point supposed that somebody might have killed him. And since he had a broken bone in the head, it was supposed that somebody hit him with some tool, which killed him. And, well, this remained as a mystery. I don't want to tell you the final exit. I only advise you, if you want to study, just go and study this. It's a very interesting item, which was finally dealt with the technique of computer tomography, computerized tomography. Now, well, there are many other diagnosis methods. I stop here with them, but I can advise you, if you want, to look at the magnetic resonance. There are many other processes, and more are coming. Now I want to go from the diagnosis to the cure of tumor in this case. And I'll show you one of the methods which came not so recently, because it was pioneered tens of years ago, but it's still in a development phase, because I will tell you why. So it's a method which Italy was one of the pioneers in the beginning. Then it was lost, and now finally came back with a facility to do this type of therapy. It's called the Hadron therapy. And strangely enough, it's shooting with an accelerator on a person to cure a tumor. So what we do in this case is take an accelerator, not any accelerator. So it's not that we can do this with Daphne, for example. The accelerator should be purpose-like built. So it's a special accelerator where you use beams of protons or of different type of ions, generically called hadrons. Hadron, a particle which is a hadron, means that it suffers strong interaction. This means hadron, strong interaction. Differently from electron. Electron is not a hadron. It only has electromagnetic interaction. So in this case, you shoot with a beam of particles on a person where a tumor is located, and presumably you cure that tumor. Not you cure. Actually, this is a wrong way. You destroy it. So you destroy the tissue with the tumor. Now, of course that this method, since I told you the word destroy, it's very, very efficient if the tumor is very localized. So it doesn't work for extended tumors. If the tumor, it's in metastasis, or it involved a too big region or a too big organ, this method, at least for the moment, it's not so efficient. For localized tumor, it's instead one of the best you could do. And I'll tell you, I want to show you why it works. So what's different from the normal chemo and radiotherapy? Now, here it's missing something, but I will tell by voice. In this curve you can see here, it's not very well seen, but okay. So this is the destructive potential. So on this vertical axis you have the power to destroy the tissue, function of the depth since the entry in the body. So here you see, after 5 centimeters from the entrance in the body, something, and I'll tell you after what it is, destroyed whatever is before like that, whatever is after like that. In a normal radiotherapy uses either photons or electrons to cure the tumor, so it uses beams of particles, but not hadrons. Uses photons or electrons. The destructive potential looks like this. So if somebody has a tumor 10 centimeters inside the body, you use, of course, the radiotherapy. You indeed destroy the tissue of the tumor, but you destroy a lot of other tissue. And this is the main reason for which who is doing the radiotherapy is suffering that horrible disease of radiation. So losing the hair, losing losing energy, losing everything, because it's practically destroyed not only the tumor, but everything else. That's one of the reasons for which when a person has to do a radiotherapy, the quantity of radiation which is given, it's a very delicate factor. And the doctors usually think a lot in order to advise somebody to do this, because it should be high enough to have an effect on the tumor. But it should not be too high as to kill the persons. And every now and then this happens. So a person might die from the radiation before dying from the tumor. Now, with red, you see what happens if instead of normal radiotherapy, you use protons. So when you shoot on a person with a beam of protons, you still have some destructive before the tumor. But you see that you have here a huge peak, which in this case it's positioned after almost 15 centimeters. But you can choose the energy of the beam and move it wherever you want. So for protons which are having smaller energy, you can shift this peak here. So you can really control the place where the destructive potential is released. And this makes a huge difference for the localized tumors. So if this is localized, if it has only an impact on some centimeters, with some of this treatment session, you can really cure it. Here in green, somebody might wonder, in green there are the carbon ions. So the carbon ions, if you want, are even more efficient if the tumor is very small. So if it involves only 1 or 2 centimeters, it might be better to use the carbon. Carbon is still somehow delicate because differently from the protons, it still leaves some energy afterwards. And I have colleagues who are doing research in this sector. So what happens by using carbon ions or fluorine or oxygen? So even this, it's a very active field. So there are many accelerators built in all over the world. This is the last comer, namely a facility in Italy near Pavia, which is called CNAO. This is, let's say, a layout, a schematic layout, where an accelerator was completely built and dedicated, started to work about 1 year ago to treat patients with localized tumors, especially in the head and neck region, but not only. I now ended with the sector of medical. It's not exhaustive, it's only an indication and some examples, because I want to go to some other sector. And among these, one of the most fascinating ones, at least for me, is the art. So there are many ways in which the science and physics in particular can help in art, either to unveil mysteries which would have remained there forever, not for this type of analysis, or even to help to cure and to take care of some important work arts. Usually what happens, this is again a general method, you use a beam either of X-rays of particles coming, for example, from an accelerator. Near Florence, there is a lab of INFN, LABEC, it's called, dedicated to this type of research, and in Catania there is some other. So we irradiate the artwork, painting, statue, or whatsoever, with this beam of particles, and we measure what happens, either what it is reflected or what it is transmitted. And the information somehow only, similarly with the computerized tomography, allows us to learn many things. And I'll show you some examples. Usually what happens, what we do, is we take, for example, a painting. This is one of the nice paintings of Lasseur. And irradiating it, we can immediately know the composition of the colors. So we get a spectrum where, which tells us each material, each atom species, it's defined by its own energy. So this is a signature, the energy of the X-rays emitted after being absorbed. So I irradiate it with X-ray tube. Then some other X-rays are coming, but these ones are absorbed and emitted by the atoms. So I can know what the painting, what the colors are containing, which is the composition. Here you see a lot of lead, some iron, some gold, some chromium. Why this is important? Well, this is extremely important because time and time ago, each painter was doing his own recipe, and this was a big secret. So not like today, we go in the shop and we buy the colors, which are more or less standard colors. In that time, each painter was jealously keeping the secret of his own recipe. So we can, for example, unveil the fakes. If we have a series of 10 paintings which are attributed to the same painter, and actually we see the same composition, when the 11th comes, and if we see that it's a complete unmatch, even if the style might fake the style of the original artist, and let's say an art connoisseur would eventually say, oh, yes, indeed, this is Leonardo, for example. You cannot trick the physics. So unless the painter, for unknown reason, didn't use different colors, but his own ones, you can unveil this. You can even do more. You can even do more because by selecting the energy of the X-rays you put in, you can select how deep you go, like in the hadrotherapy. You can select how deep you go inside the object you are studying, and you can either go superficially and you see the first layer, or you can go deeper. And this way, it came out something very interesting, that many times, actually, at least in about 10% of the situation, usually the painters reused their own materials. And this is probably because if they didn't succeed to sell or to give, or either the person who ordered the painting didn't like it, so asked to have something changed, or you will see later on, he completely changed his mind. In this case, probably either him or who ordered it didn't like it, original face pointing toward this direction, so he repainted it with the face towards us. We have here another shocking example, actually a painting of Rembrandt, where what you see is this, what you get is this. But when you get deeper and deeper, you see something very shocking, that actually initially it was a Madonna on that painting. And probably who ordered it didn't want to buy it or didn't have money or who knows what happened. The fact is that the painter did not keep it like originally done, instead redid another painting on the top of it. And in this way, it could even be realized a museum of the hidden artworks. There are many, much more than one would be tempted to believe. Well, physics is, of course, used at least, I mean, I'm sure you know, in Italy there is the Reparto Crimini, RIS di Parma, RIS di Roma. So there are many ways in which the physics is used to unveil the crimes. So to unveil or to discover who is doing something strange or bad. And well, we start from the very basic research, like searching for the blood tracks. And this is kind of rather easy to be done, does not necessarily require sophisticated methods, because when you search for the blood, what you actually are searching for is the iron, because the blood in the red part, in the red cell, contains iron. So what you are searching for originally is some type of iron tracks. Of course, if you look on iron, so it's not so trivial as I'm saying it. But however, you look for some composites of iron and you unveil it, and then you might do some more sophisticated searches for what concerns this type of search. Now I make a mix, this should have been before. Sorry, I come back to the art because I want to show you not only what you can see as secrets from the past, but you can use it for the future. You see, there are wonderful statues. This is Perseo of Cellini, where you want, this is done on bronze. And maybe something is broken and you want to repair it. Now the bronze is known to be a combination of material. It's not pure metal. So which was the composition which was used? You can know it if you do physics analysis. So if you do physics analysis, you can see here, for example, that it contains a lot of copper, of course, but it contains some other elements as well. So in this case, you might avoid something like this to happen. So whenever you try to cure a statue, a bronze statue, putting a different type of bronze on it than the original one, at the interface between the two of them, some processes start to develop which are coming out like you see here. So it's much better if you know which was the original composition to use it and to do real art maintenance at best. And this is again helped by physics. You can see here the fact that the two regions actually contain two different types of bronze, so the materials are different, and this is not good. It might look good in 1 year or 2 years, but in 10 years, side effects start to be seen. Now, this should have been before. Now I go back to the search of crimes, and one of the things which is intensively used, not only in police or in the, well, military service or in, but in biological lab as well, is the electron microscope. So the electron microscope, it's a device which instead of light, it's using an electron beam. The electron beam, the light, why this? Because with the light you can arrive to see details up to some point. Smaller details, you can't see an atom with the light. You need something which has a finer definition. For those who know what I'm talking about, I'm not going to go deeper, it's the wavelength. So the wavelength of light, it's too big to see object below some dimension. You need to create beams, in this case of electrons, which have a smaller wavelength, so they are able to touch and to see more details. And in this case, you use the electron microscope to see the shotgun powder. So whatever, if you shot with a gun, it will remain on your finger. You can wash yourself forever, and on your clothes, it will remain these very, very, very micrometric spots of dust from the process of shooting. And this remain there, whatever you do. So that's what they usually do with the electron microscope when they check for the tracks of who was eventually shooting. Another impressive application of modern physics is the GPS system. Maybe some of you know, some of you don't, but the GPS, which is helping in localizing our position with a precision which nowadays it's impressive. So you go on the street, you might search for a localizer, and this gives you indication, go left, go right. If you'd have tried to do this many years ago, so when this method was pioneered, you wouldn't have been able to. Because when people, actually the GPS, it's using a system of satellites, and your device is connecting to at least 3 satellites. It's called the triangulation method, in order to arrive, so in a dialogue with these satellites, you arrive to build up your position. The problem is that these satellites, this is a kind of, the system which are in satellites. This is how the system works, usually. So you connect with 3 of them. The 4th of them give a kind of indicator, the time scale. And when you do this, you find out that the satellites are moving actually fast with respect to our standards, tens thousands of kilometers per hour. So in this case, you might think, and this is true, that the relativistic effects starts to be important. Actually, when you dig into the case, you learn that relativity is becoming really important. Without corrections, which are actually done inside the memory of a GPS, without correction of relativistic effects, you could throw your device, because you'd be wrong by 100 meters. Can you imagine what a disaster would be? So the device itself is doing corrections due to the relativity in two senses. One, due to the fact that they are moving. So there is a certain velocity, and this velocity has to be taken into account in order to make the time corrections. The second effect, which is actually much bigger and somehow much more impressive, at least to me originally, since the satellites are farther away from the Earth, the gravitational field that they are feeling is smaller. So then the general relativistic effects take over, and which means that the time is passing differently if the gravitational field is very intense with respect to the gravitational field which are less intense. And you need to correct for this. So since satellites feel less gravity than we on Earth, you have to consider this and correct the different clocks which are ticking differently in the gravitational field. By the way, a side comment related to this. In the extreme case of a black hole, the clock, the time, arrives almost to be stopped when you arrive at the so-called event horizon at a black hole. So it's again an extreme relativistic effect generated by the general relativity. But this is a must. So your localization devices are working because they take into consideration the relativistic effects. Another application which dates back to Einstein. So do you know for Einstein got his Nobel Prize? Loud. Yes. So he got the Nobel Prize for the explanation of the photoelectric effect, which is what those who choose the Planck constant tomorrow in the lab are going to do. So you are going somehow to do the photoelectric effect and go back with the mind and with the spirit of what used to be the early days of quantum mechanics. So Einstein got his Nobel Prize in 1921 for explanation of this effect which looked rather crazy, the photoelectric effect, meaning that if you send some light on some piece of metal, you came out with the electrons. This is not crazy in any way said like this. What was crazy is that it didn't fit with the idea that the light was a wave. So now I don't want to go in details, but it brought into physics the idea that light is done of particles, of photons. But since there are effects where light is known to be a wave, it came a crisis. What means it's a wave or a particle? So it came back to the root of quantum mechanics, this particle-wave dualism, which we are still fighting to come out with an understanding. You will have a kind of a presentation related with not only quantum mechanics, but what quantum mechanics can do in the future Friday by Fabio Sciarrino. And you will see eventually some more related to this. Okay, the photoelectric effect, which looked to be, well, something like our search for string. So today we look for strings. In 1900, people were not understanding a bizarre effect which looked the photoelectric effect. Now it's used. So 100 years passed, and we use it. Where we use it? In the photovoltaic effect. So when we use the sun energy, so the energy coming from the sun for getting electric current, like installing solar panels on our houses or wherever, we use the Einstein Nobel Prize. So we use that effect, the photoelectric effect, which gives us today part of the electric power. This type of effect, it's even more important here. So in the satellites, when you send far away from your satellite, how many of you have heard about Rosetta? Which is this satellite which was sleeping for 3 years, and it was restarting 2 weeks ago. It was supposed to sleep for 3 years, and 3 years was practically lost. Was sent in space, arrived at Jupiter, overpassed Jupiter, and since they want to make economy of energy and of materials, they switch it off, programming the computers to restart 2 weeks ago. And it was a big of enthusiasm of the fact that indeed it restarted, it reopened the solar panels, which gets the power for this satellite, this rover actually, which is now hunting an asteroid or a comet or something like that. So it started to head towards this rock, which is going to pass 2 by 4 kilometer an ellipsoid to come from the deep space. It's going to meet it in August. It's going to fly a bit together with it. And in autumn, it's going to send, if everything goes well on that comet, it's going to send an apparatus which plans to measure its composition. Why for? To look for signs of life, to look for molecules which we know are the basis of our life. And all these things. So the fact that we are able to do this, it's a consequence of the fact that we have understood the photoelectric effect. So it's indeed a very, very interesting use which maybe Einstein would have never, ever thought about. But this is physics, and there are many, many, many other applications. Right now, today, coming back to the research, we are struggling with understanding whatever is in front of us, and we know that we should discover. A part of the knowledge, deeper knowledge on normal matter, we want to check what is composed the dark matter and the dark energy, if existent. I want to add if existent, even if everybody is convinced that they do exist, because in the past history of physics, many times there were revolutions. So maybe we will discover something completely unknown or some surprises. Finally, since we speak about the society, I cannot avoid asking this question, which in the end is a scientific question. And one of my colleagues, Matteo Martini, will speak about this in the very last day, trying to show you some scientific answer, because this is a scientific question, answering it's then required from science. So he will go about this. This is the Drake equation. So the future, it's open. There will be many applications in the future, and part of them, I hope, will see you as protagonists. For who is interested in Italian, I just published this book a few months ago, which speaks about the modern physics. It's published by Springer. It's in Italian, and now I work on the English translation. And it gives an overview not only on the modern physics and postmodern physics, like string theory and so on, but it has about 20 chapters of applications. Some of them I showed to you today. So what the society is benefiting from the modern physics and from its outcome. So I end here. Thank you for your attention. I hope you are enjoying the masterclass, and I hope some of you will become somehow our colleagues in the future. Thank you very much. If there are some questions, loudly. Wait. Look, so here it's some calculation. So you get here the time difference, the time correction. We can pass together through the calculation. But you get, let's say, you mean, so 3.8 kilometer per second, it's 10 to minus, I don't remember, 10 to minus 5 of the speed of light. Because it's 300,000 kilometers per second. So 3, it's something like 10 to minus 5. So 10 to minus 5, it's a very small effect. But if you look on the scale distances which are dividing the satellites from the Earth, and you scale down these many, many, many kilometers to your distances, you arrive with an error of about 10 meters if you don't consider the relativistic effects, because the satellites are far. So moving relatively fast, but are far. Okay, so enjoy the evening. Anyway, tomorrow you have in the morning the 2 new experiments. I hope you registered for the group you want to go. And tomorrow afternoon there will be the visit inside the laboratory, while Friday we are concluding with some, quantum